introduction. Today I will be talking about the generalized callback insider trading problem with dynamic information. And this is the joint work with Professor Jin Ma. Okay, those are the topics of today. So first, I will introduce what is the callback insider trading model and how do we formulate the problem. And next, we will study the stochastic two-point boundary value problem. And this is the main tool we used to solve part of the problem. Okay, next, we will discuss the diffusion problem and the resulted FBSDE. Finally, we will discuss the sufficient condition for the optional control problem here. Okay. Let's go ahead. Let me briefly introduce what is the callback insider trading model. So here we consider a market that involves three types of agents: the insider, the noise traders, and the market maker. So the insiders is the one who either observes the dynamic value of the underlying asset VT or knows some information about the terminal value at time capital T. Okay. The order submitted by the insider is denoted by CT. Different from the insider, the noise traders are those people who have no information about the underlying asset, and they just submit the aggregate order of this integral form, where this Brownian motion BZ is independent from the underlying asset. Okay. And then the market maker will set the market price based on their observation about the total trade volume submitted by both the insider and the noise trader. So that is, if we denote the total trade volume by Y, then Y is the sum of KC and Z. Then the market maker will set the price as the conditional expectation form of V capital T or V small t given Fyt, where Fy is the sigma field generated by the process Y. Okay. Now we can talk about the equilibrium in this problem. So the equilibrium means, on the one hand, the insider, of course, wants to maximize her expected terminal wealth at time capital T. On the other hand, the market maker wants to set the price as precise as possible. So they will set the price as the conditional expectation form. So this is the equilibrium. And this problem was initiated by Kyle in 1985 in a discrete time setting, and then Carrie back just generalized it to a continuous time in 1992. And since then, many efforts have been made to study this problem with various types of generalization and different approaches. So for example, Danilova used the filtering as a tool to study this problem, and Biagini, who measured Brandeis and Alexander, used the fractional Brownian motion. And recently, Masundro used the conditional mean field SDE or the conditional mean working velocity of SDE to study this problem in the Gaussian framework. Okay, and among them, for me, I think the most notable work has been done by Kempe, Chetty, and Danilova, where they used the idea of dynamic Markov bridge to study this model. Okay, and this work is the one that is very close to our work. Okay. And the last one I would like to mention is done by Tokimus, Ekran, and Louis, which I find is very interesting and novel because they borrow the idea of optional transport theory to study this problem. Okay, that's all about the introduction and the literature. So now let's go back to our assumption. So in our work, we make the following assumptions. So first, for the insider, we assume that the insider observes the dynamic value of V small t simultaneously, together with a prediction of the law of the V capital T. Okay. Then they submit the order of an absolutely continuous form, where this alpha is known as the insider strategy. The terminal wealth at time capital T can be calculated as the following equation. Next, we also assume that the market maker observes the total traded volume process Y, and they set the price as the optional projection of V of the process V instead of the conditional expectation of the V capital T. Because we think since the insider can observe the V small t right now, so that will be more reasonable for the market maker to use the V small t to determine the price. Okay. And the last one is for simplicity, we just take sigma z to be 1, then the order submitted by the noise traders is just the Brownian motion. Okay, then we can consider the following system for the process of V and Y. And before moving on, I would like to mention that here we allow the underlying asset to be influenced by the market price. Okay, and the market price is indeed the optional projection of the underlying asset itself, so which makes this whole system a market loss of SDE. So which is usually hard to solve, but we took a different route. The main idea.
Let me ask one question. So here, does the market maker observe the little bit, there's a V0?
V0?
Supposedly it's known, yes.
Yes, but they don't know the V small t.
Yeah, I'm just curious. So in terms of assumption, in terms of information, why the market maker at time 0, he can observe the V, but later on he cannot? Do you have a comment on that?
Oh, let me think. Because this asset is the underlying value,
right?
Everybody can observe the price, the market price, but the insider has some like extra information about this underlying asset.
Yeah, I'm thinking of the market maker. So from this model, it looks like the market maker observes the V0, yes, because it's deterministic.
V0, yes.
At time 0. So P0 will be equal to V0, yes.
Yeah.
So that means the market maker knows the V0. But later on, we are assuming the market maker does not observe VT.
Yes.
So then practically, why later on he cannot observe, but at time 0, he can observe the V?
Because I think that because they are not the insider.
Okay, that's fine. I know in the literature, people always assume that. I'm just thinking, is there an explanation for that?
Oh, I just think they don't have the information, more confident information. Yeah.
Okay.
With a related one. So at t equal to 0, V0 is equal to P0. But later on, PT is not always equal to VT, right?
Yeah.
I think that market maker can always observe PT, but not VT. And the VT is somewhat related to the intrinsic value of the underlying asset, and which is observed by the insiders more than the general noise trader or the.
Because for math, no problem, but practically, because if you think of it, what's time 0?
Yeah.
When is time 0? Yes. So if the market maker does not observe, he does not observe. There's no time 0 in practice. It's always from today on.
Is time 0 when the IPO happens?
Okay.
Then the information for the company will be
Maybe. Okay, that's true. A true 0 time.
Yeah.
Okay.
Yeah. Thank you for answering the question for me. So can we continue now?
Yes.
So okay. So now we want to, so the main idea, as I said, this system is like a marking loss of SDE, which is hard to solve directly. So the main idea is to Markovize the whole system. So we introduce a factor process, the process X, in the way that we want to find the deterministic functions mu, rho, and h, such that the market price PT could be represented as h, t, and xt. So this is possible because both P and X are functions of the paths of the process Y. So we hope we can find the connections between those two functions in the way that we can have this relationship between PT and XT. Okay. And this process actually resembles the weighted total order process in the work done by Campy, Chetty, and Danilova. Okay. And we have one more very natural requirement, that is the P capital T should be equal to V capital T. That is because at the terminal time, the market price should be equal to the underlying asset value, because the value will be revealed to public at that time. So actually the V capital T can be observed by anyone in the market. So the price must be the value. Okay, and another reason is actually if we write down the HJB equation for this control problem, you will find that the P capital T is equal to V capital T is indeed the necessary condition for the optimal strategy to exist. So we will talk about that later. And since we require the market price and the underlying asset value should be equal at time capital T, we introduce another increasing function, small g, and we require that V capital T is equal to G of X capital T for now. And later, we will require the P capital T is also equal to G of X capital T, which will make the P capital T and the V capital T equal. Okay, and also this small g gives the condition, the terminal condition for the function capital H. So this is the idea how to Markovize the whole system. So now finally we can formulate our problem. We have the system V, X, and Y, and we have this extra terminal condition that is V capital T is equal to G of X capital T. And in this system, the functions mu, rho, and alpha are to be determined. And now we can replace the market price PT in the expected wealth by the capital H TXT here. So before this position is PT, and now we just replace it by this function. So in this case, we have a very standard stochastic control problem. Actually, here, you may find that this system is like overdetermined because we have both the initial value and the terminal relationship. But the good thing here is we have the freedom to choose a proper alpha, which will make this terminal condition hold.
So alpha is the control, yes?
Yes, alpha is the control.
So given alpha, how about the mu and the rho? Are they control or are they need to be solved?
They are not a control, but we have the freedom to choose it. So we will see later that the mu and alpha will satisfy some compatibility condition, and that's enough. So, but those are not a control. The control is the alpha, because the alpha is the insider strategy.
But who are we? We is the market maker or who are we? You say we can choose mu and rho.
Okay.
The players, the investors, or it's the research, the mathematician, you.
Yeah, I think we must be us, like the one right this. Yeah, and I think that the market maker can also choose the mu and the rho. It's kind of we want to solve this problem for the insider and the market maker. Yeah. So the alpha is for the insiders to choose, and the mu and the rho is for the market makers to choose.
Okay.
Yeah. Okay. So those are the main goals we are, like, as I just said. So there's the main goals we are going to do. First, we need to find the functions mu, rho, and h such that we can represent the market price in this way. So we do this for the market maker, and then we want to find the optimal trading strategy alpha star, which maximizes the insider's wealth. Okay, and okay, so now we assume that the strategy alpha must be picked from the admissible control set, because we want to do the Kirsanov theorem later. So we want the alpha can allow us to do that.
That's a typo, yeah. So you say you belong to that, the you admissible. It should be alpha, yes.
Yes, thank you. Yeah. Actually, we will we use the small u to denote the alpha when the alpha, the strategy is like the closed form.
Oh, okay.
Yeah, so that's the type of study, but this is the type. Okay, now, as I mentioned before, we need to solve the extra terminal condition before, the first. So this is the stochastic 2-point boundary value problem we proposed. Okay. And before actually talking about the 2-point boundary value problem, I would like to introduce the dynamic Markovian bridge first. So this is the tool used by Campicelli and Danilova to solve this problem. So this dynamic Markovian bridge is means that if we consider a process Z, which is the strong solution to this SD with a very like special structural assumptions, and then a dynamic Markovian bridge that is the X is of this form, and in the way that it satisfies the following 3 conditions. So the pair XZ is an Markov process, and the limit of xt is equal to Z capital T when T goes to capital T, almost surely. And the third one is the X is indeed a local martingale under its own filtration. Okay, this is the dynamic Markovian bridge. And the result is, they actually constructed a Markovian bridge for the Z with the structural assumption. So the X looks like this, and it has a very complicated drift form. The small p here is the transition density for the diffusion Z. Okay, and they did this because they want the X to be the local martingale under its own filtration, in the sense that the conditional expectation of this term under fxt is 0. So this part makes the whole X, the process is the fx local martingale. Okay, and we found an example that this pair, so this line, so this X and this Z, this pair satisfies the first 2 conditions here. So they are the Markov process, and the limit of X is indeed the Z. So this satisfies the bridge property, but that example fails at the 3rd condition. So our hope is, can we solve a problem like this, but without enlisting the X to be the local martingale under its own filtration? Okay, so that's why we
So from the application point of view, from the practical point of view, X is a local martingale. Is it important or not? What does that imply?
Actually, we had the same question. So we don't find where they use the property that is the local martingale. So we want to remove that one. And
So they didn't explain why they assumed that.
I think they didn't explain, but my guess is they want to study something similar to the Brownian bridge.
Okay.
Yeah, so the Brownian bridge is the local martingale, right? Okay. So they want to keep this property for some reason, but yeah, okay. In reality, I don't know. So so this is our hope, and we want to study this problem. So we want to find the process alpha here, and the weak solution Vx and alpha will satisfy the system, and more importantly, the limit of V small t minus g of xt will be 0 as t goes to capital T. Okay, and here we consider the limit here is because the alpha, the strategy, is very likely to explode at time capital T. So we can only consider the limit of those 2. And the first thing I would like to emphasize is that this problem is not an FBSDE for 2 main reasons. So first, the Brownian motions here, B1 and B2, are independent. So they are not the same Brownian motions. And the second one is the volatilities here, the sigma and the rho, are fixed. So we don't have the freedom to pick the volatility. So this is not an FBSDE problem. Okay, so the only thing we can pick here is the alpha for the problem right now. And how can we solve this problem? Okay, the main idea is the conditioning and the minimal probability introduced by Fabrice-Boudin. So let me introduce the main idea for the conditioning. So the conditioning is like a triplet, capital T, Y, and nu. And T is the time horizon. Y is F capital T measurable random variable valued in some Polish space. And nu is probability measure on that value space. So nu is the distribution of the random variable Y. Okay, and the corresponding minimal probability P nu is the probability under which the random variable Y indeed has the distribution nu. So the idea is like you give me a random variable and the distribution you wanted to have. And now I can construct a probability under which your random variable can have that distribution you wanted to have. Of course, under some assumptions, but this is the main idea of the conditioning and the minimal probability. Okay. And we consider the special case if we take the random variable in the conditioning to be Ct when Ct is a diffusion. Okay, then we can actually write out the Radon-Nikodym derivative explicitly by this theorem. Okay, and this small t is the transition of the underlying diffusion Ct. And this Ct is like we take the Ct capital T to be the random variable in the conditioning, and we can have this P nu under which the distribution of this Ct under this P nu will be this nu. Okay, that's the idea.
Sorry, I have too many questions.
No, that's fine.
So I think I understand the math here, but I don't understand the names. The first one, it looks like you just have a random variable, a measure, and they are not related. Why do you call it a conditioning?
Oh, so it's like you need to understand this whole thing like a pair. So this conditioning, because we are going to talk about some condition SDE. So it's like the conditioning is the start of the story, and then we will study the minimal probability and go on.
So from what you write here, it's not clear what condition. It's for future. Right now, there's no condition stuff, so conditional probability or condition distribution involved. Yes. Just look at triplet. Second, similarly, the minimum probability. There's no minimal stuff involved here. Yes, so far.
Conditioning is to condition such that the distribution of Y is mu.
Yeah, but that's in the theorem. I mean, from that definition itself.
The definition is to find the P mu, such that the under P mu, the Y distribution is mu.
Yeah, but that's in the bottom. Yes, is that a theorem? Yes.
No. You are given a Q. You find the P mu. Given under Q, you have a nu.
But you look at what it's written. There's nothing about that. Yes. It's just a random variable Y, probably measure nu. That's it.
I think maybe the.
Or you missed something?
No. It's like the conditioning is
Mu. Yeah. So
actually I need to write.
There is some problem in writing.
Yeah, I need to.
Q should be distributed.
Because actually without the special case, you can always write down this P nu. And the definition, you can write down the P nu as the integration of some conditioned expectation and dq. So the conditioning part is in the definition for the P nu. So probably I need to write the P nu.
Yeah, so probably you write more. Otherwise, right now it's just a triplet and there's no connection.
Yes.
Yes.
Y and the nu even are not related.
You shouldn't try relate the T, Y, mu omega F Q. Separate them.
Yeah, also the minimum one, also maybe you need to say a little more because right now we don't see why it's called a minimum.
Yeah, Fabrice-Boudin called it minimum.
Yeah, because actually you can find several probabilities that satisfies this property maybe, but this exactly one, this P nu actually minimize the L2 norm. Yeah, so that is why it's the minimal probability. Yeah, I will write down more. I will put down more.
Okay.
in
Or
the
maybe
future.
you can switch the order and then to say.
Ah, yeah, thank you.
Because
For the
if
suggestion.
we just look at the top part of the slide,
Uh-huh.
because it's kind of irrelevant, the name and
Oh.
the description afterwards. Huh? Oh, that looks nice.
Thank you. Thank you. Yeah, okay. Thank you for the suggestion. Yeah. Any other questions?
Don't ask any more questions. We already got enough questions.
Okay, so now we have a very interesting observation from the theorem I just introduced. So remember that the theorem, the main idea of the theorem is for a random variable and for distribution, we can construct a probability such that the random variable can have the distribution, right? And here for our problem, we kind of hope that the V capital T is equal to G of X capital T, almost surely. So the first step is we want to construct the distribution for the V capital T and the X capital T. So it's like we treat V capital T and X capital T to be a two-dimensional random variable. And we construct the diffusion by the distribution for the random variable, and then we can have the P nu. We can have the probability. So the distribution we want to construct, it has the property that it only concentrates on the graph of G inverse. Okay, that means, so if this is V capital T, and this is for X capital T, and we hope V capital T is equal to G inverse, but let's just change. Capital T, and we have the graph for G inverse because it's increasing. So now we want to construct a distribution on this R2 such that the nu only concentrates on the graph. If the nu only concentrates on the graph, then the resulting P nu will have the property that the V capital T is equal to G of X capital T is 1. That's the idea. So we want to construct the nu such that it only concentrates on this graph. So this is the main idea. And here, this nu also keeps the property that the V capital T, the distribution of V capital T is the M star. Oh, I forgot to mention the M star. So the M star is the distribution for V capital T. So remember that we assume that the insider also has the prediction for the distribution of the underlying asset at the terminal time. So the M star is fixed. The insider knows the M star. So we want to have the probability in the way that the distribution of V capital T is also M star. Okay, that's how we construct this nu. Yeah. Here, once we have the distribution nu, we can write down the Radon-Nikodym derivative by the theorem, and then we can apply Ito's formula to have the following two properties. So first, the Radon-Nikodym derivative, this phi will satisfy this PDE, this equation, and then if it will also satisfy this differential equation. Okay, if we denote those two parts by θ1, θ2, we observe that those are the Gaussian kernels. So we can use the Gaussian kernel to define two Brownian motions, to define two P nu Brownian motions. Just apply the Gaussian theorem, and in this way we have this SD. So we know that the process V and X will satisfy this SD under the probability P nu. And now look at the form of this SDE. We recognize that this part, this θ2, is very likely to be our alpha, right? But we have an extra θ1. So the last thing is to get rid of that θ1. If we can get rid of the θ1, we just take the alpha to be the theta 2, we can solve this the stochastic 2-point boundary value problem. So, okay, as I said, the last thing is to get rid of the theta 1. And actually this part is not that interesting, so I will like skip this part, but I will introduce the main idea. The main idea is we use the stopping time, the sequence of stopping time tau n to truncate the theta 1. And we can obtain a sequence of solutions V, X, and P. And then we just send n to infinity, and we show that the limit is actually the weak solution we are looking for. Okay. And we also show the uniqueness in law for the weak solution. Otherwise, it's meaningless to discuss about the expectations later. Okay, so that's the main idea. So just trust me, so we can get rid of the theta 1. And by doing this, we have 2 pages. Okay, so finally we can have this main result. So the main result shows that this 2-point boundary value problem is solvable if we take the alpha star to be that form. So the phi is the Radon-Nikodym derivative, and this phi can be put down explicitly like this and satisfy this ill-post PDE. So far, so good. Any questions about this part? Okay, because now we have the alpha star. Okay, we have a strategy. So we will move on to solve the problem for the market maker now. So we need to find the price. Okay. So now we just fix the alpha star. So fix the alpha star, and we recognize that this system Vx and y is indeed an nonlinear filtering problem, with V and X being the 2-dimensional signal process and the Y being the observation. Okay, if we recognize this is the filtering problem, we can apply the FKK equation to get the SDE for the market price P. Okay, we just apply the FKK equation, and we know that the market price is governed by the SDE. This SD. But in this SD, we have like the random coefficients. So we make another assumption. So if we assume the drift for V and the strategy U, so since now we denote the alpha star to be the little u, because everything is Markovian, so and this is deterministic. So U is a deterministic function, and this function has the affine structure. So if we have those affine structure assumptions, we can simplify the SDE for the market price P, and everything is deterministic now. There's no random coefficients in this SDE, and this is superlinear. So the last thing is we just combine the SDE we just derived for the price P with the factor process X. We can obtain an FBSDE. With this terminal condition, P capital T is equal to G of X capital T. So recall that we have solved that stochastic 2-point boundary value problem. We picked the alpha star, which satisfies the G of X capital T is equal to V of V capital T already. So now we study this FBSDE to guarantee that the P capital T is also equal to G of X capital T, in a way that we can guarantee the requirement that the market price is equal to the underlying value at terminal time. So that's the idea. Okay, and look at this FBSDE. We can have the function h. We can obtain the function h immediately because the function h is indeed the decoupling field of this FBSDE. Okay, which satisfies this PDE, and the terminal condition is the h at capital T is equal to the function small g. Any questions? So in this way, we can determine the function h, which is the decoupling field for the FBSDE. So okay, this is a more general FBSDE without the affine structure. So if without the affine structure, we still have the FKK equation for the market price, which whose coefficient is random, but we can still have a FBSD. But now here the decoupling field is random now. So instead of like H satisfying a PDE, this H will satisfy an SPDE. And since the H is random now, which will add much more difficulty for us to solve the optimal control problem later, because this H is in the cost function. So we will go back to the affine structure. We will go back to study the problem under the affine structure assumptions.
In 20, it's decoupled, yes. The X does not depend on P and Z, right?
Yes.
So it's decoupled.
Mm-hmm.
Y is given, yes.
Why? Yeah.
Right, Y is given.
Yeah. Y is the observation. Everybody can observe Y. Mhm. So now, the last thing is. Let me check. Oh, so the last thing is, we have the alpha star, which solves the 2-point boundary value problem, and we have determined the function H. So the last thing is to show that the alpha star from that problem indeed maximizes the wealth. Okay, so this is a very interesting fact. So let's assume the B is 0. Okay, when B is 0, then V is a martingale. And we can show that in this case, if V is a martingale, the market price P is also a martingale under a different filtration Fy. And then since market price is a martingale, which makes the function H satisfy this PDE. It's like it forced the right-hand side to be 0 for the PDE. Since the right-hand side is denoted by the small h is 0, that forces the alpha star to take the form like this. So the alpha star will be a form like U1 times Vt minus Pt. And this U1 is known as a trading intensity in literature. And this strategy is known as something like play with the price difference. Okay. So we have this main result. So we have this theorem. So in the case when B is 0, we have the weak solution, and we have the equilibrium for this problem, because we can show that this alpha actually maximizes the terminal wealth, and the alpha takes this form, and H satisfies the PDE in the previous slide. Okay, and okay, now we have the compatibility condition for the function mu and rho. So that is saying that if the mu and rho satisfy this compatibility condition, then the whole thing is the equilibrium we have found. So let me explain. How can we show that? So this is a sketch of the proof. Okay, so we just consider a characteristic PDE for the function J. So J will satisfy 2 differential equations and 1 very special terminal condition. And we show that if this function J exists, so if this exists, we can simply apply Ito's formula, and we can represent the expectation of the terminal wealth by the difference between those 2 terms. And the first term is actually a constant because we have fixed the distribution for V capital T, that is M star. So the first term here is determined by the M star. So we want to maximize this term is to minimize this one. Okay. And to minimize this one, just look at that terminal condition. We know that the function J will be minimized at time capital T at the point when this V capital T is equal to like a G of X capital T. Because this function will be 0, will only be 0 when this position is equal to G of this position. So that's, in this case, we know that the strategy alpha, which solves the 2-point boundary value problem, is indeed maximizes the wealth if we can find this function j, right? So now we need to find the function j. So the function j can be constructed in this way. Okay, and we follow the idea of Jin Wu and consider this function, and it is easy to check this j satisfies the second PDE, the second one here, the second PDE, and this one also satisfies the special terminal condition. So, and now we plug in this function j into the first PDE. It should satisfy. We can get the result that if mu and the rho satisfies this compatibility condition, then the j is well defined. Then j is well defined, which makes the alpha is the optimal one. Yeah, that's the main story. And the last point I want to make is this compatibility condition is not that new because it is indeed the generalized version of the compatibility conditions in others' work. So for example, in campaign training techniques work, they require, so their H must satisfy this PDE, and this is the compatibility condition for rho because their mu is 0. Okay, if we take mu is 0 from our compatibility condition, we will get this one, and this one is their small f. So our compatibility condition is not like from nowhere. So I think, yeah, that's all for my talk today. Now, any other questions?
Any questions? I gotta listen to it.